So this is the Chapter 3, Lesson 2, Least Squares Regression Line, describing relationships between two variables. So please pay close attention to the guiding question. How can we follow a pattern from a data set in order to extrapolate or predict other values? So basically, how can we use our data set to make predictions of values that aren't included in it? So let's talk about regression lines. So a regression line is a straight line that describes how a response variable, y, changes as an explanatory variable, x changes. So we can use it to predict values for y or x by substituting these values in for x in the variable and then predicting the response variable. So here we have some data and we have a regression line that predicts fat gain from non-exercise activity. You can see we have a best fit line that comes down through the data, and the idea of the best fit line is to be as close to all the points as possible, meaning having the smallest amount of residual or distance from the best fit line. So interpreting it, y hat would be our predictor. That's the value we're trying to predict, a response variable given a value of x. And it has the same a plus bx form that we've used before, where b is the slope, the amount by which y is expected to change when x increases by 1 unit, rise over run, all that. A is the intercept, meaning if x were 0, the predicted value of y. So keep in mind that the slope here of this regression line does not determine the strength of the relationship. So you could have a strong relationship and a positive association of 1, but a small slope, a slope of 1/10. The association is how well the data fits the regression line. The slope is just the pattern of how our explanatory variable affects the response variable. So the slope doesn't affect the strength of the relationship. It lets you know how much your independent variable, we don't use independent, but we do use that in science. We use explanatory variable, how much that affects your response variable. So most commonly we'll use extrapolation. We'll use this best fit line to extrapolate or predict interval values outside of our data set, or values that we're interested in that aren't necessarily included. Because our data can often have these errors and our best fit line is a result of that data, predictions are often not accurate, and we'll talk about how we measure that accuracy. So we measure the accuracy by residuals, the difference between the observed value of the response and the value predicted by our regression line. So observed response variable minus the predicted. So the difference in y, what it really is, minus y hat. Remember, y hat is our predictor. The least squares regression line of y on x is a line that makes the sum of the squared residuals as small as possible. So again, we square because we don't care if it's positive or negative. We want the distance from the line to be minimized. So the distance squared is how we minimize that in order to make the best fit line. So a true best, the ideal best fit line, would have the sum of all these squares, the areas there, be the smallest. So this is a nice visual to keep this in mind. And again, we use the squares because we don't care if it's above the line or below the line. We just want a line that is as close to the points as possible. So this is what we talk about when we talk about squared residuals. They're literally squares. And the area represents summing all those up. And the line that's closest, that provides the smallest total sum of those squares, is the ideal least squares regression line. And here you have the formula for the line, as well as r squared, what it equals, and the sum of the squares, 30.9. So you can see we have a moderate association, a positive association, and the sum of the squares is 30.9. That means you add up all those areas, and that gives us the line that has the smallest sum of squares is our ideal best fit line. So our equation is given here. This is for an explanatory variable y with n individuals, the number of individual data points. Calculate the means. We represent the mean of our x by x bar, the mean of our y data set by y bar, and the standard deviation, s sub x and s sub y, of the two variables, and then measure their correlation r, as we talked about in 3.1, Chapter 3, Lesson 1. So it's the line with our predicted value y hat, where it equals a plus bx, with the slope b equals r times the standard deviation of y, s sub y, divided by the standard deviation of x. So from these data sets. Remember, we can use one variable statistics to calculate these values on our calculator. It makes the whole thing a lot easier for you. And then the y-intercept would be a equals the average of our y bar, times b times x bar. And I'm sorry, that's y-intercept A equals y bar minus b times x bar. So this is a subtraction sign, not a multiplication or division. So A equals y bar minus b times x bar. Here you can see where the mean pack weight is represented in blue, our least square regression line going diagonally. The mean body weight is x going up. Remember, these things would be centered around this mean. So a residual plot can tell us how well our line fits the data, how well our regression line fits the data. So here's our data in the regression line. This over here is a measure of the residuals. So it gives us an idea of where the average is, where the line is, and each of these points represents the distance from the line. So being up here being above the line, down here being below the line, the distance representing being further and further. So ideally the residuals would be smaller, meaning close to this x-axis and y-axis. Okay, so the residual plot shouldn't show an obvious pattern if our association is linear. If a curve pattern pops up on that residual plot, then the relationship is not linear. It could be a squared, a binomial, it could be to a higher power. So our residuals should be somewhat small in size if our regression model is good. Ideally we want small residuals, meaning our data points aren't far from our regression line. The standard deviation of the residuals is very important. So we want to have, our standard deviation is the square root of the sum, remember this little symbol means adding up all the residuals squared, divided by n minus 2, because it's an estimator. So, and then that equals the distance in y. So our value minus the predicted. So this is the actual value minus the predicted. We add up we square them and add them all up. We divide by n minus 2, and then we take the square root of that whole value. So that gives us the standard deviation of the residuals, meaning the average distance of our residuals from the regression line. Okay, r squared is known as the coefficient of determination. It tells us how well our regression line fits the data. So it equals 1 minus the sum of the residuals squared divided by our standard deviation of y. So SSE over SST. This gives us a good sense of how well the line fits the data. We'll go over this more in class. Some general guidelines here for using correlation and regression. So some general advice. The distinction between explanatory and response variables is key for regression. It's really important. When we looked at correlation, we could switch the two because it didn't matter which was on the x-axis and the y-axis because we're just looking for an association. When we're looking for a predictor, because the regression line is trying to minimize the y value, our goal here is to have the smallest distance between our predicted response variable and what we actually get. Because that's the goal of regression, then it makes a big deal what we say the response variable is, because those predicted values and the ones we actually get, we want the difference between those to be as small as possible. So if we switch them, we'll get a different equation. And if we reverse them, we would get a different line. So correlation and regression only describe linear relationships, so always do a quick scatter plot as we discussed in class. Our work doesn't hold up if the relationship isn't linear. So outliers are falling outside of the overall pattern that we see. In the y direction, but not in the x direction of a scatter plot, they'll have larger residuals. So for these, because we're trying to minimize the distance in the y direction, we're worried about our predicted value, the response variable. They'll have large residuals. So we're worried for regression about outliers in the y direction. Other outliers may not have as large residuals. Observations are influential for calculation in stats if removing them would markedly change the result of the calculation. So removing a point would really change our result of our regression line. Then they'd be called influential. Points that are outliers in the x direction are often influential for the least squares regression line. So one big thing to keep in mind, association does not imply causation. An association between explanatory variable x and response variable y, even if it's very strong, is not by itself good evidence that changes in y causes changes. Changes in x cause change in y. So think about the analogy of AP stats or AP calculus classes and global warming being correlated, that as over the years AP calculus classes have increased and over the years global temperature has increased. That doesn't mean AP calculus caused the global temperature increase. So correlation is not causation. So there's a lot of formulas in this lesson. It's much more complicated than 3.1. So I encourage you to really read over the examples in the book, look over the summary, and really read this closely in your book to get a good sense of it, as well as looking at the outline that I'm going through now. So which of the following here's your multiple choice. Which of the following regression lines, regression line 1 is here, regression line 2 is here, has the smallest residual? So choose the best answer. And this is something you don't have to calculate, but I want you to just have a good sense of what we mean by residual. They each have best fit lines, and here are your 5 options. So go ahead and pause right now, read over the lesson, and go over these things in your book so you have a good sense of what they mean and looking at more examples, and then answer the multiple choice and free response below.